I'm really pleased to introduce our next speaker, Pierre Paulin of Synopsys. Pierre has had a long and distinguished career in the electronics industry, and currently at Synopsys he's been leading the effort to develop Synopsys' new embedded vision processor. And Pierre is going to talk to us about another aspect of low power vision, which is detecting and tracking faces. I think I may have mentioned in my opening remarks this morning, I've seen some really super low power implementations of face detection and face tracking. And I think when you think about the Internet of Things, thermostats and all kinds of devices, what they can gain from knowing that there are people around, knowing that there are people paying attention to them, being able to track the people around them, can potentially be very valuable in making those devices smarter and more responsive to the people around them. So Pierre's going to tell us a little bit about some work that Synopsys has been doing in that direction. So please welcome Pierre Paulin.
Good afternoon. Boy, it's a pleasure being here and seeing that last talk. I'm the guy on the weekend who does the vacuuming, so I'm thinking this is tremendous productivity saver and this is going to make my weekends better. However, being also interested in vision, I probably will spend more time with that vacuum machine, observing it and playing with it than I would saving the vacuuming that I normally do on the weekend. Anyway, it is nice to see those real case studies of vision. I'll talk about another case study here, face tracking. I'll start off and say this is one of the rare talks that does not have CNN in the title. So I do need a little logo saying CNN inside. I will be talking about CNN as part of this presentation, where we're combining kind of classical tracking, learning, and detection algorithms, integrating CNN technology in a low power accelerator to create new variants of TLDs that integrate CNN. So there is a CNN inside in this talk. So I'll start the talk out just kind of introducing the embedded vision algorithm pipeline. For most of you here, this will be just a reminder. We'll quickly look at the actual face tracker application, which we started with the tracking, learn, detect, and adapted that, integrating CNN into that application. Of course, we would like to map this onto an embedded platform, so I'll describe our target embedded vision processor and the programming environment, which is based on OpenVX, the Chronos standard. And then we'll look at, once we have explained this algorithm and the platform, how do we map it and what are the challenges there? And then what are the lessons learned? So very quickly, just to say Synopsys at a glance, started out as an EDA company, has diversified into EDA for verification, for design, for silicon design, and more recently for verifying software. And also has a key, big part, which is IP, intellectual property, and we are part of that organization. And of course, as part of that organization, we're leveraging a rich pool of IPs. In particular, we're using the ARC-HS RISC processor, AXI interfaces, DMAs, memories, and so on. We're also making use of the Synopsys HAPS FPGA-based rapid prototyping system. Some of the numbers about the company, roughly 9,000 employees, $2 billion company. So a very quick reminder for most of you of the vision algorithm pipeline and how Face Tracker fits into this pipeline in a minute. First, the first stage is typically a pre-processing stage, and these two examples here, noise reduction and color space conversion, is typically part of your ISP pipeline. And then you get into the more vision-oriented, such as scaling, Gaussian pyramids. And then once you've processed your image and scaled it, you then get into selecting areas of interest, detecting objects, subtracting backgrounds, extracting specific features, segmenting your image into different areas of interest, and things like connected component labeling are examples of this selecting areas of interest. Then we get into, once you're into the area of interest, you then do precise processing. And that can be recognizing a specific object that you've detected from a previous frame temporally. Could be tracking an object through space, matching specific features, and higher level functions like gesture recognition, where you're doing a combination of these things and a high level interpretation. And then finally, the last stage is more control-oriented, high-level decision-making, analyzing motion, for example, once you've done segmentation, you recognize that it's an arm and a hand, and you recognize the motion of the arm and hand through space. You do an analysis and say, that's a hand wave, or that's a stop now, or raise the volume, or whatever else. You're typically making decisions on positive matches or negative matches, and flagging high-level events. So that's a very simple view of the vision algorithm pipeline. As I mentioned, there is a CNN inside. So where does that CNN fit? It really is about object recognition and object detection. But as you've heard in the lovely, the wonderful keynote this morning, CNNs can be used quite widely. And in fact, we're seeing them used in more abstract use cases. So I put in dotted line here that CNNs, in many cases, can complement or even replace many of these other classical functions that are used in R&D and vision up to 2012. And we're seeing this CNN taking more and more space. So let's look at the example that we'll be discussing today. It's a video surveillance type application where we're trying to first find a face, distinguish it from other faces, and track its movement through space. This I discovered accidentally from some of my colleagues in India. These are two famous Bollywood actors, apparently. I just took them from a random web search. So this is a really nifty application. If you're a Bollywood star stalkers, this is the application for you. In any case, this was an accident. The purpose of the talk today is really about the stages in this and how we use CNN as part of the stages. So the first stage here is the grayscale, where you're first taking an image, converting to grayscale. Most vision operates on grayscale. Then you create a pyramid, where you take your image and you downscale it to different layers so that you can have scale and variance in your object detection and tracking. Then you get into a phase where you've detected faces. You want to actually distinguish a specific face. So in this case, we want to distinguish the right-hand side actor in green and track the motion of that person through space for your favorite stalking exercise or whatever it is you want to do with this application. So I'm going to go into more details of the algorithm, so let's just skip ahead to the algorithm. So we started with OpenTLD, which is well known in this community. TLD stands for Tracking, Learn, and Detect. And so we have a very simple block diagram here illustrating the main phases. So the first phase is grayscale conversion. And then you enter two parallel paths. So there's a tracking path at the top and a detection path at the bottom. And then there's a fusion where you're making some decision on what is the most reliable estimator of the image that you want to track, of the face in this case that you want to track. So the bottom layer starts with using integral image. And the information for the integral image is used in the next phase, which is a multi-level detection cascade. So let's zoom in on the detection cascade. So in OpenTLD, there's 3 steps, and the idea here of a cascade in vision is that you do a first detection, which is very low cost, but lower accuracy, and then you're trying to eliminate, with a very low computation cost, obvious candidates that are not going to be the face you're looking to detect. And then you go to a more precise but higher compute power second stage, which in this case is an ensemble classifier, and then you go to the third. If that is still positive, then you go to a third, even more discriminating stage, but that costs more to compute. So the first stage is very simple. Using the data that came from your integral image, you can do a very simple measure of variance. And the idea here is that any parts of your image that have very low variance are things that you are, for example, a white wall, a gray wall, or a very non-variant. It's something you can't track anyway. So that it's one, a lousy candidate because you can't track it, and 2, it's very unlikely to be a face because no one has a simply non-variant face. So that's a very easy one. And the good news there is that you can use integral image to do this measure very quickly. Then you get to something more sophisticated, and this is called an ensemble classifier. Excuse the French accent from my name, so I know how to say ensemble the right way. So ensemble, for those of you who have not heard it in French before. And this is based on an approach that's based on random firms. This is basically you have your current patch of your image that you're trying to evaluate whether this is a good candidate. You're trying to evaluate a probability that this is the face you want to track, so you're looking at a specific patch. And then you're comparing against a set of previous patches that were detected, and they were taking typically 10, 12 random points and taking them in pairs against your current image and your saved previous images, and there's a database, or a set of those. And then you're doing pairwise comparisons and doing normalized cross-correlation. So it's basically a difference in the pixel intensity. So if both of them are kind of medium gray with a small variance, that gives you a high probability. You do that for all 10 points, and then you get then you have a threshold. You say it is a good match or it's not a good match. So that gives you a binary vector, let's say 10 digits, and that becomes a code, and you store that, and you create a set of these probabilities, and that gives you a global probability. And from that, you say there's a threshold. Do I reject? If it's over 60% probability, for example, I accept, and if it's under 60%, I reject. And if you do accept it, then you get into the third stage, which is even more compute intensive, and this is based on nearest neighbor classification. And there, here you have a different set of learned images. So you have a set of positives and negatives that you're storing dynamically as you go through this process frame by frame. So you had a set of recognized positive elements and a set of negative elements that is also used. And you're basically doing a normalized cross-correlation of the distance between those two elements. And so this is also a dynamic approach, and there's a learned process, which we'll get to in a minute, that is used to feedback from the previous iterations, and you're updating the set of positive samples and negative samples, and then doing the normalized cross-correlation. So going back to where we came from, if I can do turn, yes. So we looked at the cascade. At that point, you're going to have a set of candidates, and then you'll choose from that candidate what we call non-maximum suppression. These are usually overlapping windows, and you'll choose the best candidate. And then you have the top phase, which is happening in parallel. And in OpenTLD, this is based on the well-known PKLT, optical flow, and that's the K is for Canada-Lucas Tracker, pyramidal Canada-Lucas Tracker. And what that does is looks at the previous image and looks at the current image for the area of interest that you're focusing on, and determines whether this is the previous image is moved in space, and looks at the path and the similarity. At that point, you have a candidate as well, and you have a probability attached to that candidate. And you can the way you measure that is use the same normalized cross-correlation calculation at the bottom layer that's used in your nearest neighbor calculation. Use the same exact calculation to then do a fair apples and apples comparison in your fusion, and then you pick the highest probability one. The highest probability one then goes in to update the database of the fern tree and those binary values that represent your probability that this is the same image, and you update the positive and negative samples from that best example, and then you reiterate. So this is, of course, a dynamic process. So that learning data goes back into both stages of the detection cascade. That's the algorithm. Let's now look at how we've taken that idea and said we now have a new technology based on convolution neural networks, and we have an accelerator for that technology that some of you may have seen the presentation this morning that my colleague Bruno Lavigueur, also pronounced in French, presented this morning. And so we want to exploit that. This is a low-cost, low-power implementation. We said, let's explore some of the ways we can combine this classical approach with a CNN approach. So what we've done here, there's two areas where we're introducing some changes. First is we're introducing a CNN in the middle of this pipeline. And on the bottom side, we're first identifying CNN. You can set a high threshold or low threshold. That is based, a high probability this is a face or a lower probability. So the first thing we're doing is we're going to simplify the detection cascade. Rather than using a detection cascade on the entire image, because we have this low-cost, low-power CNN face detection, we simply know where most of the faces are. So we put a low threshold, make sure we're not excluding anything. And then typically you reduce by about 3/4 in most test cases the amount of pixels you actually need to analyze. We only highlight the places where there are likely faces. Sometimes they're not faces because the threshold is low, but that's fine. You're simplifying. And then you do your detection cascade classically using the same approach as before. On the top side, we're using the CNN with a higher threshold. There we want to make sure it's a face, and we want to track that face. Here, rather than using PKLT, because of the dynamics of this whole algorithm and the fact that we have high confidence it is a face, we can use a more lightweight context tracker. And there we're using a variant of Contra, which is another well-known context tracker. And we've actually simplified that. Even we've taken Contra, which is less complex than PKLT, and simplified that. Contra uses what they call supporters and distractors, and we only need to use the supporters in this case because of the fact, again, that we have a high confidence that it is a face, and we can use that for the context tracking. So those two parallel paths run in parallel again. And then there's a non-maximum suppression as before, and the fusion, we use the same normalized cross-correlation on both paths, make a decision on the best one, augment the learning database in exactly the same way. So it's a very somewhat minor variant. The main change is, of course, the PKLT being replaced by Contra, and the detection cascade working on a very small, or typically 25% of the image, because you've recognized where faces are likely to be. The detection cascade is the same as before. The only difference, of course, is that you have the CNN at the front of the stage here filtering out all those areas that are not faces. Otherwise, it's exactly the same. So we now want to map this onto an embedded processor. So this embedded processor is a combination of two types of processing elements. So a classical RISC core, so these are the Synopsys ARC-HS cores running at 1 gigahertz on the left-hand side. And then we have this new CNN object detection engine. This is a set of 2 to 8 processing elements that's configurable that are focused on multiply accumulates and convolutions, as Bruno presented this morning. And I won't describe that today, just to say this is a optimized low-cost, low-power engine to accelerate CNN. They communicate through shared memory, and data movement is managed by a DMA. So that's a very simple view of this processor, which is the target for this application. Of course, we need to program this, and so we're using the recently proposed standard from Kronos called OpenVX. OpenVX is provides two things: a set of standard kernels, which I'll get to in a minute, but also provides an environment for composing a data flow graph, essentially, and describing the dependencies between a set of kernels. So here we have 5 kernels, a kernel UI that has data that is read in, and there's a dependency on UJ and KJ, and so on. So this is a composition of 5 kernels, and is expressed using the OpenVX standard. Now, OpenVX also defines a set of standard kernels. So this graph is composed of kernels, and those kernels can be of 3 types. The first type, of course, is you want to make use of the standard kernels that are available in the OpenVX library, so you can use those. You can also define your own kernels, so we support the OpenVX provision for user-defined kernels. So those kernels are composed in the graph, and the function of those kernels are expressed in standard C or C++. And finally, you have these new CNN kernels, which can be encapsulated as a user kernel in the OpenVX terminology, but they encapsulate a face detection or a hand detection or a pedestrian detection or whatever it is that your standard library of CNN kernels is available. So that's a very quick view of the programming environment and the target platform. So let's now get back to our application. So this is a face tracker application running 30 images per second, doing a single face tracking, so multiple face detection and single face tracking. This is at VGA resolution. So looking first, of course, is how do we map this? We have to do the profiling. So looking at the amount of giga operations per second, the 2 biggest ones are the detection cascade, which is 4.5 GOPS, and the PKLT tracker, which is about, plus the state estimation, combined are about 1.5 GOPS. So that's 6 GOPS of a total of just about 7 GOPS for this VGA at 30 frames per second. So it's clear that these 2 functions, if you want to optimize this application, very clear that that's where you want to focus. So let's look at this same graph, but with the new, incorporating the CNN function in the middle of it. Again, these separate functions are pretty low computation. Key thing here is that your detection cascade, which was 4.5 GOPS, what we've measured on average for all the benchmark we run is that it's about on average 1 GOPS because of the fact that you've used your CNN engine to filter out all the areas that do not contain faces. You're only doing this cascade on the high likelihood area. And the second point is we're replacing the KLT tracker with this Contra-based simplified tracker, and that's another factor of 3 reduction from 1.5 GOPS to 0.5. So the CNN doesn't cost any GOPS on the RISC machine. Of course, it costs GOPS on the CNN. I'll get back to that in a minute. But the total GOPS here, we went from about 7 GOPS to a little under 3 for this application. And of course, there's some GOPS on the CNN, quite a few of them, but as we'll see, they do not cost very much nor consume much power. So just going back one step, sorry. Oh, wrong button. Yeah, okay. So this is our graph as you express it logically. The good news in OpenVX, you pretty much capture that graph pretty much with the same decomposition. We simply regrouped the last elements because they're actually, although complex in terms of what they do, the non-max suppression, the fusion, the learning, is actually not a lot of compute power. So we've grouped them into a single node. Otherwise, the other nodes are pretty much the graph as we saw it before. So this is the actual program that we run. And how do we group these? It's fairly straightforward. The combination of these together is a little less than 1 GOPS, so that will fit on one processor. So these are ARC HS RISC cores running at 1 gigahertz. So 1 GOPS it fits it with that. The detection cascade is also close to 1 GOPS, so that fits on another RISC processor. And the other functions are a little less than 1 GOPS, and so that's on the third processor. And of course, the face detection itself, which is captured in OpenVX, is actually a remote procedure call, and this is handled by the runtime and tools. This is invisible to the programmer, but of course that is offloaded to the CNN and runs on that engine. So let's look at the implications. If we look at the original OpenTLD, as we said, it's a 6.8 GOPS. Which would mean if we were using the standard ARC HS RISC cores, would require at least 7 cores. No CNNs here, and the total area of that is about a little less than 3 millimeters square, and consumes about 200 milliwatt. With the CNN, we're at a lower number of GOPS for the RISC. However, we have other GOPS running on, so that would require a minimum of 3 RISC cores. We have a CNN, which in this case requires 2 processing elements to implement those GOPS. This is scalable from 2 to 8, but in this example, 2 was sufficient. The area of that is the total area, combining both the RISC cores and the CNN engine. The CNN engine itself is about 0.7 millimeters square for those two processing elements. And we have 3 RISC cores instead of 7. So the total area is 1.8 instead of 2.8, and more importantly, the total power is about a factor 2 better. So very quickly, what are the lessons learned? We've incorporated a CNN into a classical approach based on TLD, and that allows us, first of all, to filter out the areas where a face is not present. And that gives about a 4x reduction of the compute cost for the cascade computation, which was the single biggest component of the TLD. We also have been able to, because of the fact we have high confidence it's a face, we've been able to use a less complex feature tracker than PKLT, so we use a contra simplification. And that is another 3x reduction of that specific cost. So those are the 2 highest costs that we've been able to reduce quite a bit. Clearly, as in TLD, tracking context is important, so it's not enough to just have a CNN to find faces. You need to be able to distinguish these faces. So that's to make sure your bounding box, that the green box that you're tracking a specific person, is kept around that. And finally, as a result of combining this heterogeneous architecture of standard RISC processors with this optimized accelerator, overall, we get a 30, even though intuitively there's more GOPS because these are very specialized GOPS, but there are more of them. But they're running on a very specialized low-cost, low-power engine that only does that. And so that overall, for this combined application, it's about a 33% area reduction. And possibly more important in the embedded space, 100 milliwatts for a face tracker at 30 frames per second is an interesting number for many, many target spaces. And the other implicit message here about CNNs is that in the keynote we saw this morning, we were talking about GPUs and high-end machines. This is also showing that you can use CNNs for much smaller graphs and much lower cost and power and still get very good results. The number we presented this morning, F1 numbers of over 90%. Using these very small graphs and very small machines. And of course, we're leveraging this same graph in this combined implementation, combining TLD and CNN. So I put some references here to both the TLD work, of course, the famous CNN presentations, Jan LeCun last year. We, of course, have a website and a booth, so you're welcome to come there, and I'd be happy to take any questions. We have 4 minutes. I'm on target for once.
Well done. Questions for Pierre? Put up your hand. Do you have a question? So I have a question, Pierre. I have a question, which is, you talk about like 90% accuracy. What applications are satisfied with 90% accuracy?
So in looking with CNN, especially this year, there's this kind of single-minded driven, I won't say obsession, but anyway, single-minded driven approach to get that extra 93, 94, 95% accuracy. And this is, keep in mind, to obtain 95%, we're talking about really, really large machines. Well, one for the training side, but also for the implementation. We're not talking 100 milliwatts and a couple of millimeters square. The other thing, historically, so it's not realistic to achieve this with low-cost embedded machines. Historically, you have to look back. If you look at these face detection benchmarks, if you look at FDDB, and we look at the old classic Viola-Jones, is something like 67%. And that Viola-Jones or HOG are in the 70, 75, 80, 85%. Some of the better ones are approaching 90%. But there's a lot of industrial work out there that works very well with 80 to 90% range. So we're getting into, for the class of examples we've done with face detection, we're at that 90%. If we look at FDDB, we're actually comparing, FDDB is a very difficult one. The world's best FDDB result is about 90%, and that's using a super GPU. So that's kind of the high end. If we look at the top 20 and we say, let's look at the kind of the middle 10 of the top 20, which are really based on high-end GPUs and really good results, the average of that is 84%. And we're getting somewhere at 82% currently. So it does show that we're able to get close to the state of the art. And second, these 80% for FDDB or 90% for more realistic databases are numbers that are much better than the classical approaches like HOG and Viola-Jones. And in practice, in industry, these are sufficient. We won't win a contest of 96%, but we will hopefully sell some products.
Very good. Any other questions for Pierre?
Hi, Pierre. I'm just wondering if you can control the environment where you see the face, and you have that person stop, take the picture or whatever, and then move on. How accurate can you be then?
So if the person stops, if there's no motion?
Yes, like say that we're in a car coming into a parking lot and they had a stop at the gate and you were taking their pictures as they came in there. You could control the light, you could control just about everything. How accurate could you be in that case?
So there's two parts to that. So first there's the detection accuracy, and yeah. CNNs, you can train a graph for a database of images with high light variance and luminosity differences. Yes. And also, the graph we're using takes faces sideways from front, and we create through data augmentation, create a whole rich range of conditions. So that's independent from our technology, the implementation. That's a CNN strength, is that you can really train for a wide range of conditions. And there's effort and compute power to do that, but once you've got that, you have a graph. It can be very scale intolerant through the image pyramid and luminosity tolerant through the training. Then there's the tracking itself, and
Here we're not trying to, in the benchmark we've done, we're very close to the OpenTLD in terms of the tracking accuracy, combining Contra with the CNN compared to PKLT. But we're not actually trying to sell a tracking algorithm. We're just using that as a means to show our customers how you could combine CNN and classical approaches, provide a programming example so that then when they want to use our tools, they have something to play with. So I can't answer that accurately, say, are we better than PKLT, and how, it wasn't our purpose here, was not to do a vision algorithm, was just to do a demonstrator. So just to clarify what our intention here is, not to do a new, but we have researchers nearby that will try to take this and then go publish on the vision side. So maybe in the next few months we'll have some publications on that.
Thank you very much, Pierre. I'm afraid we're out of time, but if you have other questions, I think Pierre will be around the rest of the day. Thank you again, Pierre, for a really interesting presentation.